Hi, in this video we'll take a look at this Hantek 1833C LCR meter. If you recall, I reviewed a Hantek 2D72 oscilloscope on the channel last summer, and that scope, which I have it here as well, is conveniently of the same form factor. In fact, if you look at them side by side, you will see that the cases are essentially identical. Even the front panel button layouts are identical between these different products, except for the input sections down here. This kind of uniform design is not a new concept. It not only reduces the R&D cost, as products now can share the same overall layout, but also helps build a brand identity if it is done correctly. I have many Keithley products in the lab, and they all have the familiar brownish boxy look and feel. Some of the key-size scopes and signal generators in the educational series nowadays also follow the same principle. Of course, if you look at the top here, you will see that there's quite a bit of empty space, and this is because we don't have any BNC connectors on this LCR meter like we did with the 2D72 oscilloscope. If you press on it, I'm sure you can probably see that, you will see these pre-molded holes for the BNC connectors because this case is essentially the same as the one from the 2D72. Anyway, this LCR meter was provided to me by Banggood. If you are interested in the product after watching this video, please be sure to check out the product link included in the video description below. By the way, there are two versions of this LCR meter. One is the 1832C and the other one is the 1833C that I have here. It looks like there are only a few differences between these two models. One is that 1833C has a few more test frequency ranges, and the other is that the signal level for the 1833C can be switched between 0.3 volts and 0.6 volts. Everything else between these two models are identical. And it seems that some people have suggested on the EV blog the differences between the 1833C and the 32C are only at the firmware level. So in theory, you could just buy an 1832C and upgrade it to the 33C yourself if you are adventurous enough. Now, whether or not you need a dedicated LCR meter is totally dependent on what you do. If you are mainly doing digital circuitry, you probably don't need a LCR meter. A cheap eBay component tester like this one will serve you just fine. If you don't need an inductor measurement capability, you can even get by with just a decent multimeter. But if you do any serious analog work, like working with switching power supplies and DC-DC converters, having a dedicated LCR meter will be necessary as it gives you the precise frequency conditions at which the components are measured. Without further ado, let's power it on and take a closer look. Oh, I didn't realize that the screen protector is still on. We will have to remove it first, otherwise you won't be able to see the screen that clearly. And by the way, you do get this nice hard shell carrying case. Inside you will find a pair of these short alligator clips and a calibration clip here. Now let me power it on. And you notice just how fast it booted up. This is actually a good sign. One thing I like about this meter is that it's extremely intuitive to use. And because it has all these buttons, you can get to the same selection in multiple different ways. So for instance, right now I can use the first row of the buttons here to change between the resistance, capacitance, and inductance measurement mode, so on and so forth. And the same functionality can also be achieved by cycling through this button here. I can cycle it through capacitance, inductance, and the general impedance measurement. Of course, there's also an auto-ranging capability here. So that is the multiple ways you can do it. And also we have another secondary functionality button here that you can use it to cycle through different measurement for your secondary display here. So right now, for example, we're in the resistance measurement mode, and we can also do the ESR. Now, of course, these two readings will be the same in this mode, but you get an idea. Now let me zoom in just a little bit so you can see the display hopefully a little better. We also have this secondary row here. You can use this to control the ranges here. For example, I press frequency and you can use the up and down, or just use the frequency button to cycle through the different frequency measurement. And also can press the range and you can change it from auto ranging to a specific manual ranging. The level, of course, we have two levels on this 1833C. You can change it to either 600 millivolts or change it to, by press it again, to 300 millivolts. Again, the buttons down here also do the range changing as well. So you have many different ways to do that. Now, there's a speed at which your measurement is taken, and we have a low speed and medium speed and high speed. Now, I don't recall there's any compromises amongst these different settings, but I gotta think that for high speed you are sacrificing something. So not entirely sure why you would choose a slow measurement versus a high speed measurement in this regard, but I suspect that is probably the stability of the readings and also the accuracy, but nevertheless that's not specified on the user manual. So if anybody knows the differences here, make sure you leave a comment in the comment section below. And one of the last items here you will see is the equivalence mode. This one is either in series or parallel. To achieve accurate measurement, you will need to make sure you choose the series and parallel mode correctly. Now, here is the general rule of thumb. For low impedance measurement, you generally want to use the series mode. Low impedance includes small resistance, small inductance, and large capacitance. The parallel mode is used typically in high impedance measurement. For high impedance, that includes large resistance, large inductance, and small capacitance. Let's first test out the resistance measurement mode. In this mode, we can measure resistance from 0.4 ohm all the way up to 20 mega ohm. And you will notice that the resistance measurement actually is jumping in the mega ohm range. Right now we don't have anything connected, but you can still see there's some kind of erroneous reading from that resistance. So clearly, this meter probably shouldn't be used to measure extremely high resistance. Also, you can see the accuracy is dependent on range as well. Its best accuracy range is at 0.25% at below 10 kilohertz, between 400 ohms and 400 kilo ohms. But the accuracy can be as bad as 9% in the 20 mega ohm range. And you can see that because we're actually jumping all over the place. In fact, if I increase the frequency, you will see that this measured resistance is actually jumping all over the place, even without anything connected here. So clearly, this is something you need to pay attention to. And in my opinion, this meter probably is not best suited to measure high or very large resistance. But nevertheless, for smaller resistance, it shouldn't have any issue. So now we're going to measure a few resistors using the 120 Hertz frequency. And the first resistor we're going to measure is this 0.1% 100 ohm resistor here. And by the way, I had already calibrated this device using the calibration bar that is supplied with the unit. And all I have to do is to press that in and press this cal button. Now it does take quite a bit of time to run a calibration, so I'm not going to do it here. As you can see that we're showing as 99.94 ohms. That is actually in line with the 0.1% accuracy here. Right now you can see that the resistance measurement, we have a resolution of 10 milliohm. And in its lowest measurement mode, I think it's 0 to 0.3999 ohm range, that resolution becomes 0.1 milliohm, which is actually quite impressive. Now let's test a 100 kilo ohm resistor. You can see that we're reading 98.34 with no problem. One neat feature this LCR meter provides is the ability to compare different values and give you whether or not the value is within tolerance or out of tolerance. That comes in very handy when you're trying to bin the components here, so I'll demonstrate that. So right now, if I press the compare and hold, essentially this would be my reference component here. So right now you can see that the tolerance is set at 20%. So let's set the tolerance to, let's say 5%. So for that, if I swap in a different resistor here, also 100 kilo ohm, you will see, compared to the previous measurement, now we have a variation 1.75%, and this is still good because we are essentially giving it a 5% tolerance. So let's measure a few more. This one comes in at 99.94 1.23, which is a 0.77%. So if we change the tolerance back to, for example, 1%, this one is within range, and the other one would be out of range, I would assume. Yeah, you can see that this is 1.7%, 1.8%, and it says no good. Using this functionality, you can use it to easily bin your components and select the components within a specific tolerance range. And next we'll check out this capacitance measurement mode. And for that, I'm going to start with a very small capacitor. This is a 22 picofarad capacitor. And in the capacitance mode, we can measure all the way up to 20 millifarads. The accuracy is between 0.4% in the mid-range all the way to 8% at the highest ranges. What is impressive is that at its lowest range, 0 to 3.999 picofarads, you have a resolution of 0.001 picofarad. So that gives you a lot of resolution when you are measuring small capacitance. So right now the measurement frequency is 40 kilohertz, and we'll leave it at that. Let's zero out the residual capacitance. And I'm going to plug in this 22 picofarads capacitor here, and it's measuring at 24 picofarads. And that number is probably accurate enough. I do want to double check that capacitance measurement, so let's actually change the frequency to a frequency that I actually have on my Agilent 1731. So that let's change it down to 1 kilohertz. So we're measuring at 24.6. Of course, the resolution dropped in this frequency range, but it's 24.5 or 0.6. So now let me use the Agilent to measure the same capacitor. And you can see we're measuring at 24.7. So the results are exactly the same. Here I have a 1000 microfarad or 1 millifarad Nichicon capacitor here, so let's take a look. And right now we're in the series measurement mode with 120 Hz as our measurement frequency. You can see that the measured result is 1 millifarad. And here's where I will show you, if you change the series to parallel, you will notice there is going to be some discrepancy. So right now it's parallel, you can see the measurement result is ever so slightly different than the series measurement result. And it's important for you to know when to use a series versus a parallel measurement to obtain the most accurate result. And of course, while we're in capacitance measurement mode, we can also change the secondary measurement. Instead of dissipation factor, we can take a look at the equivalent series resistance. And in this case, for this specific capacitor is 0.13 ohm. And by the way, I forgot to mention, like all LCR meters, this meter also has a guard terminal right here. And it comes in handy when you are measuring high impedance components like the small capacitors like we measured a little bit earlier. Now I have demonstrated its use in my review and teardown video of the Agilent 1731B LCR meter, and I will put a card up there if you wanted to check it out. In essence, the guard holds the potential at the same level as the signal, and thus prevents any leakage current flowing from the signal carrying conductor to elsewhere, most likely ground. Therefore, the stray capacitance can be eliminated. Now let's move on to the inductance measurement range. In this range, we can measure inductance all the way up to 1000 henries. And of course, the range and resolution is frequency related. At its lowest measurement range, which is 0 to 4 microhenries, you have a resolution of 0.001 microhenry, which is very impressive. So let's take a look at that in action. Right now, I'm setting it at a measurement frequency of 100 kilohertz. And let me hook up this small inductor here. And in fact, let's actually zero out the readings first. So we have a stray inductance of 0.4 Henry. Let's route it out. And now let's measure this inductor again. Now we're showing this is roughly a 1 microhenry inductor. And here is the same inductor measured on my Agilent 1731B, you can see it's 1 microhenry. Of course, right now we're at 1 kilohertz frequency, so we don't have as much resolution on this meter compared to the Hantek. While we're at it, let's measure another inductor. This time it's a larger inductor. This one comes in at roughly 600 millihenry. And for that, let's first set it up. Because this is a large inductance, we wanted to use the parallel mode. And also, we wanted to change the frequency down. Let's change it to 120 Hertz. That should be good enough. And now let's do the measurement here. It is probably always a good idea to zero out your readings first. But because we're measuring such a large inductor, I don't think it matters that much. So let me zero it out. Here you can see it's only in the microhenry range, so we're not going to worry about it. So for this inductor, let's take a quick look here. And you can see that we're reading about 660 millihenry. As I mentioned earlier, the accuracy is highly dependent on the range and also the frequency you're currently doing measurement under. So in order to understand the reading, the accuracy you're currently at, you really have to refer to the manual. Another neat feature of this meter is this record button. What it does is to allow you to record the readings over a set period so that you can figure out what is the minimum, maximum, and average reading in that time interval. There's also a dedicated button for setting up the meter, and you can see the language, you can set it to auto power off and backlight intensity, and finally the last power on state. And of course, you can also see the model number, which we're at 1833C. From the software version, you can see that this is relatively new from the end of last year, and the hardware version is version 1. If you recall, when I reviewed the 2D72 oscilloscope, when it was powered off, it was drawing something like 1.6 milliamps current. Now, it seems that the same issue happens with this Hantek LCR meter. Right now, we have it powered off. You can see we are drawing about 1.6 milliamp. This parasitic power consumption is, in my opinion, a little bit too high for a handheld device like this. Even though the LCR meter comes with these two 18650 lithium-ion batteries, each is rated at 2.6 amp hour, given this capacity rating, in 3 months, you will run flat with this 1.64 milliamp current draw. Now let's power it on. So it looks like the operating current is actually very low. So given this, you can run this meter continuously for a couple of days without any issue. This LCR meter can also be remotely controlled by PC using SCPI command via the Keyside Connection Expert. The user manual has a list of all the commands you can use, and here I'm just demonstrating a couple of them. Most of the time though, you probably will just use the LCR meter as a standalone, but knowing that it supports SCPI command is definitely a plus. The 1833C also comes with some rather rudimentary PC software. I unfortunately could not get it to work on my Windows 10 VM, as it refused to connect for some reason. But interestingly, the SCPI communication worked flawlessly. Now I have the unit fully disassembled. You can see that we're essentially having a 2-board design. One board is for the keypad and the other one is the main circuitry. So let's take a look at the keypad one first. I have to say, compared to the 2D72 we reviewed a while ago, the board design is definitely much simpler in this LCR meter. And it doesn't seem like we have a lot of components on this board. On this end, you can see there is a section for a DC-DC converter, probably the charging circuitry as well. And on the other side, there's really just space for the keypad. There's nothing else. Just like what we have in the 2D72 teardown, on this unit, we also have the USB-C port mounted on the side, which is pretty far recessed. Although the case has the designation for SD card and USB connector here, of course we have this power connection, which is the USB-C, but on the board we don't see any designation of the SD card, at least on this side. Now move on to the main board. As you can see on the back of the board, there's not a whole lot going on here either. Here we have two lithium-ion batteries in parallel, and these are the same as what we see in the 2D72. They're connected on the positive sides together, and on the negative side, these are individually switched by these MOSFETs by the look of it. Towards the far right, we have a buzzer and a couple of programming headers. Towards the top here, we have an unpopulated device footprint. By the look of it, is an SD card. Interestingly enough, though, the orientation of the SD card does not match the opening on the side. So not entirely sure if they had any plans to include this SD card in the future, or it's just a common design that was actually left it in place. And by the way, if I remember, I will upload the high-resolution pictures onto my website and leave a link below so you can reference these pictures at your own leisure. Towards the other end, we can see there are these diodes between the two input terminals. At least two of the diodes are back-to-back. These are presumably the protection diodes. Now flip it over. You can see on this end we have a STM32 compatible microprocessor. Judging from the circuitry we can see on this side of the board, it is very apparent that most of the functionality is implemented in that microcontroller, as there's very little supporting circuitry here. On this side of the board, we have a few op-amps. These two are TL9062. These are reel-to-reel op-amps. And we have two other op-amps. These are 808032 high-speed op-amps. Then we have quite a few of these SGM3002. These are the electronic switches scattered around on this board. Underneath here, we also have a CD4051, that is a MUX, and by the look of it, its output is connected to the guard. So let's buzz it out. You can see that these are the outputs, pin 1, and this is the guard terminal. They are connected, so there's some kind of a switching mechanism to connect the guard to the internal circuitry by the look of it. And that's pretty much all I wanted to cover in this review and teardown video. All in all, I think the Hantek 1833C is a fairly decent LCR meter to have in the lab. I hope you enjoyed the video and learned something new. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel. I will catch up with you next time.